Welcome to Data Structures and Algorithms, the Egg Edition. Today's topics are stacks and queues. Stacks are an abstract data structure that can be built as a special version of a linked list. In stacks, duplicate elements are not allowed. Therefore, these eggs have all a different color. What makes stacks special is that inserting and removing elements is only possible at the top of the stack. Initially, the size of a stack is 0, so the egg box is empty. A stack has two important pointers. For this, I borrowed two surprise capsules from the surprise eggs. The first important pointer is the origin pointer. That points to the stack's origin. The second important pointer is the top pointer that points to the stack's end. As soon as I insert the first eggs, purple, blue, green, the top pointer updates always the address related to the last inserted egg to indicate the top of the stack there. How do you execute operations in a stack? A stack has two main operations, push and pop. Pushing means a new egg is inserted at the top position. After inserting one egg, the address in the top pointer is adjusted so that it again points to the most recently referenced location on the stack. So pushing happens in constant time with big O of 1. For removing the most recently added egg, I use the pop operation. The egg that is at the location pointed to by the top pointer gets deleted and the stack pointer gets adjusted. The complexity is also big O of 1. Easily pushing and popping the top element are the benefits of stacks. Because pushing and popping of elements is only possible at the top, the egg I put in last is the first one that I can get out. So the insertion sequence counts here. This principle is called last in, first out, LIFO. Inserting or deleting of elements in the middle of a stack are not standard operations. Stacks do not allow random access, so accessing a specific egg is complex as you would need to traverse the list. So the access operation takes big O of n. Also, when searching for a specific egg, in the worst case you would need to check it by popping egg after egg, which could become complex with a big O of n. In summary, stacks are useful when the most recent element is most important. For example, when you want to undo an action in a program or reversing a word. You push a given word to stack and then pop it letter by letter from the stack. Let's move on to the second topic, queues. A queue is a basic data structure, just like a stack. In contrast to stack that uses the LIFO approach, queues uses the FIFO, first in, first out approach. That means that inserting of elements can only happen at the rear and removing of elements at the front of the queue. Initially, the size of a queue is 0, so the egg box is also empty. Also, a queue has two important pointers. The first important pointer is the rear pointer that points to the queue's beginning. The second important pointer is the front pointer that points to the queue's front. As soon as I insert the first eggs, purple, blue, green, the rear pointer updates always the address related to the last inserted egg to indicate the rear of the queue there. The front pointer remains unchanged. How do you execute operations in a queue? A queue has two main operations, Enqueue and Dq. Enqueuing means a new egg is inserted at the rear position. After inserting one egg, the address in the rear pointer is adjusted. Enqueuing happens in constant time with big O of 1. For dequeuing the egg that was first in, I use the dq operation. The egg that is at the location pointed to by the front pointer gets deleted and the front pointer gets adjusted. The complexity is also big O of 1. Easily and fast enqueuing and dequeuing elements are the benefits of queues. Inserting or deleting of elements in the middle of a queue are no standard operations. Queues do not allow random access, so accessing a specific egg is complex. The time complexity of this operation can become big O of n. Also, when searching for a specific egg, in the worst case you would need to check it by dequeuing egg after egg, which could become complex with big O of n. In summary, queues are useful when the first element is most important. For example, in systems where requests are processed by a handler, the incoming items are stored in a queue, and when a handler is free, it takes the new item from the queue and starts processing it.